Right, so this will be a talk about properties of tensors that are preserved under taking linear maps, and rather than proving any very detailed specific theorems about such properties, I'd like to try to explain a little bit what such properties look like when you evaluate them in very high dimensional vector spaces. Okay, so we work over a field, and most of the time this is going to be a field with Q elements, a finite field. And if you have two tensors, say S and T, let me put them in different spaces. Right, so I have a finite dimensional vector space over K and another finite dimensional vector space over K. And I have tensors in this tensor power and this tensor power. And I'm going to say that S is less than or equal to T if there exists a linear map from W to V such that phi to the tensor power D applied to T is equal to S. And then we also say that S is a restriction of T. This terminology comes from the fact that you can think of these as multilinear maps from the V star to the tensor power, V star to the D, the Cartesian power, to the field, and then this is like restricting a tensor to a subspace, at least if this linear map here is surjective. Okay, and so we're going to be interested in properties that are closed under such restrictions. So let me give that a name. So a restriction closed property X is just is the data of an X of V sitting inside V to the tensor D for all V, for all finite dimensional vector spaces over our field, such that for all phi, let's say V to W, phi to the tensor power D maps X of V into X of W. That's what a restriction closed tensor property is. And we've seen many examples already in this conference. So for instance, we have seen the partition rank. Not going to do anything with this definition, so with this notion, so I won't define it, but if you bound this by some fixed constant, then that is certainly something that is preserved under taking linear maps. And similarly, you can do this for ordinary tensor rank, or you can do it for subrank. So subrank is always very difficult. So subrank is the maximal R such that it, so the subrank does not have this property, right? Subrank is the maximal R such that your tensor restricts to this guy. So that being, well, okay, so it does. So subrank being at most, something is preserved under this. Subrank at most K. You have to be careful. For some notions it's probably not true, but certainly analytic rank at most some number. The analytic rank could be some real number because there's this logarithm. So let me put at most some real number here. And there's more things you can do. These all look kind of similar, but there are other types of restriction closed properties, like for instance being symmetric. Just this being a symmetric tensor. If this is a symmetric tensor, which means it's preserved under permuting the tensor factors, and so is this one. And of course, for the same reasons, Q-symmetric. or as Andrew was mentioning, you could take some interesting Schur functor, and that would also be preserved by linear maps. So there's all these properties, and then there's another source of restriction closed properties, namely not having a given tensor T0 as a restriction. Yeah, if you have a tensor T which does not restrict to T0, in the sense that there's no linear map that sends it to this, then also this guy does not map to this guy, because otherwise you could first take this linear map and then this linear map. And so this is what I'll call a forbidden restriction. Okay. Yeah.
Why can't we apply different linear maps to different tensors?
Yeah, that's a good question. So if you're, that's right, if you're interested primarily in multilinear form, that's the natural thing to do. And everything I'll say will work in that context as well. So so then you're allowed to take D linear maps. But yeah, but for instance, if you want to think about polynomials or so, or symmetric tensors, this is the right thing. Right, so we have seen many of these notions already in previous talks. So for instance, Briet had this question to which I don't know the answer, but I want to repeat it because I think it's a very good question. So if the, let me say, if the slice rank, or yeah, slice rank would be another example, but let's say if the partition rank of a tensor T is equal to some number C, and this tensor has coordinate, lives in a tensor space of this form, so with equipped with coordinates. That was important for Job's question. So does there exist a subset of the coordinates here, of the numbers 1 up to n, such that the principal subtensor, let me write it like this, also has partition rank, well, maybe not equal to C, but let's say at least some, maybe I should have called this different. Let me call this R, and let me say some constant, at least some constant times R, and we want this S to be some other constant times R. Yeah, so in other words, if you have a big tensor that has a high partition rank, but that has some partition rank R, can we find a linearly sized subtensor that also has them? And I guess we don't know the answer to this, and what I'll say today also doesn't give a precise answer to this, but it does give some sort of quality. Right. There's a theorem that I wanted to mention, and then I'll start describing what we've recently done. It's a theorem that Andrew already mentioned today in slightly different terminology. Namely, if you have a f in, let's say, s to the dv, so this is now about symmetric tensors, and the characteristic of the field is either 0 or bigger than d, and k is finite or algebraically closed. Okay, and now, so these are not conditions on f, obviously. If this f over here has high Schmidt rank, which is the same as the strength that Andrew mentioned, then it restricts to any d for degree d form in m variables. Okay, and so the quantifiers here are like this: that there is a constant which depends only on this m and on this d, such that if a form of degree d in any number of variables has at least that constant as a Schmidt rank, then by doing a linear variable substitution, it specializes to any given degree d form in n variables. This universality of strength, this form. And so in the limit that Andrew described, this says that if you have an infinite strength form, then it specializes to any finite form. Okay, so the theorem I'd like to discuss today, and then maybe discuss some applications, is joint work with a student in Bern, a PhD student, Blatter, and a postdoc called Rogniewski. But it is very much inspired by earlier work in characteristic zero and over infinite fields with Arthur Big, Rob Effermond, and Andrew Snowden. So in a sense, what we did was take all the things we did in that setting, not all the things, some of the things we did in that setting, and try to do them over finite fields. So the setting of this theorem is you have a finite field, and you have tensors ti in vi to the tensor power d. So d is fixed in this theorem, but these vector spaces, they vary. They're all finite dimensional vector spaces over this field K, and you have a tensor in each of them. Then there exists an I less than j, such that the I is less than or equal to tj. Okay, so in other words, this says that this partial order that you have on tensors by specializing using linear maps, that's a well quasi order. That's what people call it. So let me just give you a feeling why such a statement should maybe be true, and I'll also give a proof, but and also give you a feeling why in other cases maybe it shouldn't, you wouldn't expect it. So so this theorem implies the corresponding result for symmetric powers. Same result for symmetric powers. So S to the D. And what it says then is if you have an infinite sequence of forms of degree D in maybe an increasing number of variables or not, but then there is going to be somewhere one of these forms that after a linear variable substitution specializes to a form earlier in the sequence. So let me give you a reason why that is true if D is equal to 2. So let's say that the field has characteristic not equal to 2, then if the degree is equal to 2, it's quadratic forms. They are characterized by their rank and by whether the determinant of the Gram matrix is a square or not. And so in this infinite sequence, well, if as soon as you have two that have distinct ranks, then that guy specializes to the previous one. And if they all have the same rank, then there's going to be at least two that have the same squareness of the Gram matrix. So for D equal to 2, this is a easy statement, but it follows really from this fact that that we know the classification of degree 2 forms. And already for degree 3, it's, if you think about it, it's quite remarkable. If you start writing down forms over a finite field of homogeneous of degree 3, but eventually one will have to specialize to an earlier one. Let me make another remark, and that is that in this statement, the fact that this is finite is vital, because if K is an infinite field, then no such statement like that one is true already for D is equal to 2. Now I'm talking about tensors again. So if you take this matrix, MA is equal to 1, 1, and A and minus A, you can think of this as a tensor in V, tensor V, where V is just FQ squared, K squared. Then, well, MA is less than or equal to MB. This just means that there exists a G in GL2, such that GMA, G transpose is equal to MB. But now let's assume maybe that the characteristic of the field is not 2. I mean, you can do examples in characteristic 2, but now you see that this must send the symmetric part of this matrix to the symmetric part here. So it follows that G is an orthogonal matrix. And that means that you're conjugating over here, but the characteristic polynomial here is lambda square minus a square plus a square, I suppose. So this here holds if and only if a square is equal to b square. So it's very easy to write down infinite many things that do not specialize to each other. So this is a particular feature, the way it's stated here, for finite fields. Okay, let me write down some corollaries, of which the first 4 are actually going to be equivalent to this statement, but they each emphasize a different aspect of this statement. And the first one is that every chain, descending chain, x1, x2, and so on, of restriction closed properties stabilized. Yeah, because if it didn't, then, well, you would find tensors in xi minus xj for infinitely, xi minus xi plus 1 for infinitely many I, and those would violate this well quasi-orderedness in the previous statement. Yet another way to say this is that every restriction closed property is characterized by finitely many forbidden restrictions. Again, the proof is immediate, either from this or from the statement of the theorem. Give another one. Whenever you have any restriction closed property, there is a subspace such that for all subspaces, x of v is the intersection over all phi from v to u of phi to the tensor d inverse of x of u. And that's easy to prove from item 2 here. There's another one which I think is kind of interesting, is that every restriction monotone function function on D tensors. And by that I mean, let me call this function maybe f. So that means that if s is at most t, then the f of s is at most the f of t. And so this this function, this is r value, let's say. This has a well-ordered value set. Yeah, so for instance, if you look at the analytic ranks of d-dimensional tensors, then that forms a well-ordered subset of the real numbers. Okay, I kind of indicated already why this is a consequence of the restriction, the tensor restriction theorem, as I formulated it over there. Let me also explain, for instance, why this is equivalent to, say, item 1 over here. Yeah, well, it certainly follows from it, and if you want to go from 4 to 1, then well, here you have a sequence of restriction closed properties where here is, let's say, x0, this is just x0 of v is just v to the tensor d, so it's the entire space. And so as a restriction monotone function, you could do something like, given your tensor, you look at the biggest xi in which it sits and then take 1 over that I. Okay, that would be that by 4, that would be a well-ordered function, and that means that this chain stabilizes. Okay. Then there's 2 more, one of which relates to Job's question, is that for every restriction closed property, so it's a statement like this, except with coordinate restriction. So there exists an n0 such that for all n, if t lies in k to the n to the tensor power d, and if it satisfies, well, this satisfies the property x if and only if every principal subtensor of size at most n0 satisfies. Once you have that, this means that for all x, there exists a polynomial time algorithm for testing x. Yeah, so let me comment on this. There's a famous open problem in computer science, which asks whether the so-called asymptotic rank, oh, I haven't mentioned asymptotic. Let me do that over here. So there's this notion, asymptotic rank of a tensor. T, this is going to be this is the limit for t to infinity of the tth root of the rank, the ordinary tensor rank of the tth. Oh, sorry, there's too many t's here. The tth tensor power of our tensor t. Yeah, and this is this tensor power that Harm was mentioning. You take t copies of your t and you take their tensor product, but you put the first copies of v all together in one big v to the tensor little t, and so on. So this is still a d-dimensional tensor. And the question in computer science is whether the asymptotic rank of 2 by 2 matrix multiplication whether that is actually equal to 4, which is equivalent to saying that it is at most 4 because it cannot be smaller than 4. And so in principle, there's an algorithm that would take as input any tensor and test this property. Right? And in fact, a polynomial time algorithm. Now, of course, the proof of this entire theorem is non-constructive, and it might very well be that this algorithm at some point has to test whether 2x2 matrix multiplication is a restriction of your given tensor. So this doesn't say anything new about this particular open problem, but
what does it mean to have an algorithm if your proof's not effective?
well, I mean, that might be that's not a mathematical question, right? It's a philosophical question.
It's a serious question.
No, there is an
I don't know what an
algorithm.
algorithm
I'm saying there is an algorithm because there exists an n0 such that if I want to test for any
All right.
for any tensor whether the asymptotic rank is at most 4, I only need to look at the n0 times n0 sub-10.
Stabilize.
There is an algorithm. We just don't know how to compute that n0.
It's like the situation with the graph minor.
It's like it's exactly like in the graph.
minor. With the graph minor, see, in another lecture you mentioned this. How is this related to Seymour-Robertson?
I don't, unfortunately, I don't have a way of embedding the graph minor theorem in this problem. I tried a little bit, obviously, but no, I think that requires more complicated structures.
And is the graph minor effective? I don't think so. I mean,
Well, I mean, what does that question even mean? How do you input the data? So if you say, is there an algorithm that, for instance, given a surface, spits out this finite list of minors, forbidden minors, for it being embeddable on the surface? I suppose from their proof, eventually
in
that
Diophantine equations, we face this all the time. You have a finite number of solutions to an equation, but you can't find them. That's pretty, I wouldn't call that an algorithm.
No, but this is different. I mean, the statement is here, there exists an algorithm. It's just, we don't know what it is. That's a different state.
It's disturbing.
It's disturbing, but it's a different state. Okay. Let me say a little bit about, so this was all over finite fields. And as I said, that is kind of important for this tensor restriction theorem. But most of the statements in this corollary also hold for an infinite field if you require that every property that you look at is a Zariski closed property. Yeah, so in this statement, it would be every chain of Zariski closed restriction preserved restriction closed property stabilizes, or every, well, this one doesn't have an analog because yeah, this forbidden restriction is not a not exactly a Zariski closed property or so. This doesn't have a direct analog, but 3 has a direct analog for Zariski closed properties, and 4 does not have an analog because the level sets of these functions or the sub-level sets need not be, but it does if you take sub-level sets of Zariski closed properties, and 5 and 6 also have an analog. So now I wouldn't know how to prove this this tensor restriction theorem by looking at specific tensors. I would have no idea if you give me a sequence of degree D forms, how to show that eventually you find one that restricts to an earlier one. So this is kind of, I find this very remarkable, but it's not the way you should approach this theorem. The way you should approach this theorem is via this equivalent characterization over here, namely that if you have a chain of restriction closed properties, that stabilizes it. And to prove such a statement, it seems impossible to do that by concentrating only on tensors. You should do this in a bigger class of objects, like symmetric tensors and alternating and so on. So what's the point here? So in general, this thing that sends v to the tensor d, this is a functor from vec to vec. So vec is the category of all finite dimensional vector spaces over our finite field, our finite field K. And it has one further property, namely such that the dimension of P of V, well, we can just compute it, right? It's just it's the dimension of V to the power n, to the power d, sorry. And this is a polynomial. It's a polynomial in the dimension of V. And so the entire statement, so the theorem and the corollary hold for general such functions, the functors. And in fact, I don't think it is possible to prove that statement just for this particular one without doing it for all of them. Now, this looks maybe like a much larger class, but there's a theorem that says that actually it isn't such a much larger class. This is a theorem that Andrew pointed out to me by Kuhn, which says that any such functor is a subquotient of a direct sum of finitely many of this type. So say of V goes to V to the tensor power D1, direct sum V to the tensor power dk. For some numbers D1 up to dk. So this is not a much more general statement because of this characterization of such factors. Okay. And so in particular, this covers not only polynomials, but alternating tensors or tuples of alternating tensors or things like that. Okay, so I'd actually like to give some details of the proof of this theorem, because I think they're interesting in their own right, and they show why somehow working over finite fields, well, you get stronger statements like this tensor restriction theorem and this fact about restriction monotone functions. But you also have to work harder than if you do things over infinite fields. And so the first step in this proof is a little bit unsatisfactory, and I'm not 100% sure we really need it, but we reduce to the case that K is a prime field. So that's kind of easy because if you have any functor from vector spaces over K to vector spaces over K, you can just think of that other vector space as a vector space over the prime field. And the only thing that happens is that the dimension gets multiplied by some constant. It's still a polynomial. So you still have a polynomial functor, and properties remain properties. So that's an easy statement, and it makes sure that some annoying things that can happen later with pth powers of variables, and so cannot happen anymore. And then this condition on p growing polynomially with the dimension of v, this is actually equivalent to the following statement. So there exists a d such that for all u and v, the map that p induces from hom u v into hom p u p v can be given. These are just finite sets, right? Because we have finite vector spaces, finite dimensional vector spaces over a finite field. This is just two finite sets, but it can be given. So can be described by a polynomial map of degree at most d. And if you take this d minimal, then this is called the degree of our p. So in the case of tensors, this degree is just this d over e. In general, this degree is an upper bound. It's an upper bound to the degree of this polynomial that you have over here, but it need not be equal. So now you want to do some kind of induction on this functor p, and essentially the idea is to show that that when you take some sub representation of p, and you have a restriction closed property, that either that restriction closed property is just the same thing as its projection modulo that representation and then the pre-image, or you can essentially embed it into a smaller polynomial representation. And so how that works precisely is that there exists a unique minimal subfunctor, which we call p bigger than d minus 1, such that if you mod out this subfunctor, that this becomes something of degree at most d minus 1. So this is when you're working over infinite fields, polynomial functors have a direct sum decomposition into degree 0, degree 1, and so on, and you can just take the homogeneous part of degree d. But over finite fields, there is no such homogeneous decomposition. So you have to use this definition. So it's the minimal subfunctor such that if you mod it out, then the rest still has degree at most d minus. And let me just do an example to illustrate how kind of subtle this is. So if you take, let's say that the characteristic of our field is equal to 2, and you take p of v to be the symmetric tensors in v tensor v. Okay. Then this has a subfunctor q of v, which are the skew symmetric tensors. So they are the ones of this is the span of all things of the form u tensor v plus v tensor u. I could write minus, but it's the same thing here, where u and v run through v. So these are the symmetric tensors and these are the skew symmetric tensors. And now there's a difference between whether the field has 2 elements or more than 2 elements, because if k is really the field with 2 elements, then the quotient of this by this, so the degree of p modulo q is actually equal to 1. So if you think about this, this is symmetric matrices, and this is skew symmetric matrices. And if you mod this out, you're left with diagonal matrices. Well, and on these diagonal matrices, essentially, the linear maps act by themselves because squaring something gives you the same number. But if the characteristic if the field is at least F4, or so if it's F4 or bigger, then the degree of P modulo Q is still equal to 2. Because then you're still, the way linear maps act on these objects still depends quadratically. So in this case, we would say that P bigger than, so in the first case, we get that P bigger than 1, I guess, is equal to Q. And in the second case, P bigger than 1 is just equal to all of P. So the point of this is that these polynomial representations that we are studying here, they are not really representations of group schemes. They are representations of finite groups, or even better, finite monoids, and of a finite dimensional vector space over FQ into itself. Okay. And then so then we do is the following. We suppose that you have some property of degree D tensors, or of objects in this general polynomial representation P. And I guess what's the numbering? Am I at 3 or something? 4. So if I have such an object, I'm going to think of X as a variety. Yeah, as a variety in B, or more precisely, you know, X of V is some finite subset of this finite vector space P of V, and it can be defined by some polynomial equations, because any subset of P of V can be defined by polynomial equations. So we can define I of X evaluated at, let's say, at V. That is going to be the ring of all functions on P of V that vanish identically on X. That's the vanishing ideal of X. And I'm kind of suggestively write this as a coordinate ring of something, but I'm really thinking of functions here, not of polynomials. So this is just a set of all functions from PV to itself, but to K. But of course, I can represent any such function as a polynomial, and actually such representations play an important role in the proof of the theorem. Okay, so let's see. So now, suppose that we have a sub-representation of P bigger than D minus 1. And this is an irreducible sub-representation. Yeah, so in our examples, for instance, there's not much choice, because this is the only sub-representation of this guy. So we would have to take Q equal to R equal to this Q over here. Right, but okay. So we would have to take R equal to Q. Then yeah, I kind of use these words interchangeably. Yeah, subfunction. That's right. Okay, and then I have this projection pi that goes from P to P modulo R, and I can define x prime to be phi of x. And by that I mean whenever I evaluate at some vector space, I have just a linear map from PV to PV modulo RV, and I take the image of x of and now there are those two possibilities that I mentioned before. So there's a kind of dichotomy, namely the first one. So either x is equal to pi inverse of x prime, right? So in our example, you could imagine that so x prime is going to be some property of objects in this functor p modulo q, which is just well, certainly in the two-element field case, this is just the same thing as the functor that sends v to v, and there are not so many interesting properties there, but it is some property in there, and either the R component doesn't affect on whether your tensor satisfies the property X, that is this first case, or it does. But if it does, then we can find some polynomial that vanishes on X but doesn't vanish over here. So, or there exists a vector space, the name. So there exists an F in the ring of functions on P of k to the n, such that F vanishes on x of k to the n, but not on the bigger guy. Pi inverse of x of prime of k to the n. And well, then we want to use this function to somehow show that the coordinates on R depend on in a linear fashion on the coordinates of x prime. But a priori, we don't know anything about this polynomial. We just know that it exists. So we have to do something with it to create a linear polynomial. Now, try to explain how that goes in an example. So the next step is something like we massage f into a function f tilde, which maybe uses a bigger dimensional space. So in the k of p of k to the maybe n plus m, such that f tilde is linear. Well, I should say affine linear. In the R of 0 times k to the m direction with coordinates, with coefficients, I should say, that are in k of p to the k to the n times 0. Yeah, so it's the other way around. So kind of these coordinates depend only on this this second vector, and these coordinates depend only on the first vector. That sounds kind of mysterious, but let me explain in an example how that works, and also why the finite field case is more difficult than the infinite field case in this step. So let's assume that we were thinking about a polynomial functor that sends v to v tensor v. Yeah, just two copies of the vector space v. So in this case, there's not so many interesting properties. You have things like well, I guess there are some, but you have things like these two vectors are linearly dependent. That would be a restriction closed property in this case. But suppose that for some reason, the equation f that we started with at this particular form, let's say x1 to the third times y1 to the fourth, And I'm going to assume that my field is F7. And so this lives in K of P of K to the 1. Okay. So you should think of P of K to the N as the space of 2 by N matrices. And so there's coordinates y1, x1, y1, x2, y2, and so on. And suppose that for some reason we had a property that was defined by this polynomial. That's not a very interesting property. It just means that either this one is 0 or this one is 0. That's not the point of this example. So how would we get from this equation an equation that somehow is linear in R? I haven't told you what R is. So RV is the second copy V here. So the second V. So that is this row over here. Okay. So from this equation, we want to get an equation that is linear in that second row. Well, we do things that we know from say acting with Lie algebras. So we do things like this. We act with such a matrix on our polynomial f. So now I secretly think of f as involving also the variables x2 and y2, except that they're not there. And what this would be is x1 plus s times x2 to the power 3 times y1 plus s times y2 to the power 4. Okay. Well, what would you get? Well, let's check. We first get back our equation, x1 to the 3 times y1 to the 4 plus s times, then we get 3 times x1 squared times x2 times y1 to the 4 plus 4 times x1 cubed times y1 to the 3 times, I suppose, y2, right? So far, so good. But now we're going to get an additional term here, which is the term x2 to the 3 times y2 to the 4. And then there's other terms, s squared and so on, up to maybe s, well, we won't get that far, well, maybe s to the 6 times something. And remember, we're working over f7, so s to the 7, which would be what you get when you take this term to the power 3 and this term to the power 4 is equal to s1, so that's why this term is here. And so, so you see, we have kind of half succeeded. We have found some equation that is, we have found something that is linear in this y2. But unfortunately, there is still this part which is not linear in y2. The point here is that when you look at all the coefficients of s in this expression, they are going to be themselves equations for this property x that we started with, because x was preserved under taking linear maps. And so you need a way to kind of separate out this part from this part. And it turns out that in this case, you can do that in one step by looking at how diagonal matrices act on these two. If you look at let me see, if you act with a T1 in the first column of that matrix and a T2 in the second column of that matrix, then this one scales with T1 to the 6 times T2 and this one as well. But this one scales with T2 to the 7, which is just T2 to the 1. So it scales differently, and that gives us this equation over here. Okay, so what we do in general is starting with some equation, we construct, by doing these kind of operations, we construct an equation that is just linear in the direction that we want to model out. Any questions? And then the last step in this proof is that you take h to be one of those coefficients. And what you show is that if you do the shift over k to the n of p, so I need to define what this is. So this is a new polynomial functor, which evaluated at v is just the p of k to the n direct sum v. This new functor contains the property, the shift of x over k to the n. And if you now invert this coordinate h, then it turns out that, well, this is sitting inside the shift over k to the n of p with this coordinate h inverted. But actually this maps into the shift over k of k to the n of p, and then with r modded out, and then with h inverted. And it turns out that this map over here is an injective map. Yeah, so from the fact that that we have these equations that are linear in this direction that we're modding out, we find that that by forgetting that direction, we get an injective map from our property into a smaller polynomial functor. Okay, and so this is the basic idea how you analyze properties inside this this polynomial functor p by going to smaller p. And then there's some kind of induction on this polynomial functor that allows you to prove this noetherianity and all those other consequences. Let me see how much. I don't think that's not enough. I was going to say I was going to give a second proof, and so let me just say, I mentioned this theorem by Tamar and Kazhdan at the beginning. In the case when the polynomial functor is s to the d, or tuples of homogeneous forms, and the characteristic is bigger than the degrees of the polynomials in that tuple, you can also use their theorem to prove this noetherianity statement. And essentially what you do is, if you have a property of polynomials of degree d, then their theorem says it implies that it has bounded Schmidt rank. So you have a map from some tuple of polynomials of smaller degrees into your polynomials of degree d, which hits your entire property. Yeah, so you take some sum of products, and every element in your property is hit by that map. And so if you have a sub-property, then you can pull it back along this map. And so you get a sequence of sub-properties of tuples of polynomials of lower degree. And you can continue doing this by their theorem, which also holds for tuples of forms. And so that's another proof for the same noetherianity. And there are some similarities, right? Here we go to do a shift of p modulo r. And in that proof, you also replace a polynomial by kind of polynomials that you get from it by fixing some of the variables and thinking of the other of the polynomial as a polynomial in those variables and taking the coefficients. Okay, that was not very well explained, but my time is up, so here's that. Thanks.
Oh, so you erased it, but you had an N0 up there.
Yeah.
For the coordinate restrictions.
Right.
I think Kazhdan, three tensors got a bound that's, I think, exponential in the rank. Could you venture a guess as to the best N0 you could get?
Well, I think if I'm allowed to take linear maps, which I know I'm not, but if I'm allowed to take linear maps, then I think probably just polynomial. I can get polynomial like this, but then you would. I didn't explain this bit, but how you go from taking linear maps to taking only subtensors, you need this theory of finitely generated Fi modules, and so. Well, you need some results from there, and I'm not familiar enough with the bounds that exist there. You should try it out because, okay, I mean, this is a proof, but it's a proof of one particular statement. But I guess my message is that you can use this kind of techniques whenever you have some tensor property of interest. So in the case of partition rank at most something, you can just by dimension counting, you know what is the smallest dimension n where there are equations, and then you can try to act with this kind of operations to make your equation linear in kind of in the biggest part of the tensor, and then try to use this. So what's good about it is that you don't get polynomials that involve many terms. So it might actually work well with respect to just the symmetric group rather than the general linear group. So we should try this out. I think it's a good game to play.
So your operations were the shift in diagonal matrices to make linear.
Yeah, that's right. This is a basic trick in Lie algebra. So when you have a representation of a group, you act on it with elements of the Lie algebra, that kind of raising operators, so upper triangular or lower triangular matrices. The kind of new thing, at least for us, I'm sure there's more theory that we are unaware of, but the new thing for us is that you have to be much more careful, right? So since s to the 7 is equal to s, you don't get your equation in kind of one step of acting with the Lie algebra, and in general, you have to keep on going for a while.
Okay, thank you.